So first thing that I'd like to do right now with this existing stack is that I'm just going to review my debugging messages, those debug tracing messages that I'm printing, and essentially I should probably just say that the capacity is this, right? And then the capacity is something else when we allocate memory. So so the two functions here, allocate memory and reallocate memory, that we have inside of our stack, essentially do quite a bit of work to manage the dynamic memory that we have to use. Because if you look at this picture, we're dealing with two parts of our stack, right? So this is actually some kind of binary footprint in memory, but when we think about it, this box manages this, essentially this box right here, right, that we have, manages this array of dynamically allocated integers. And occasionally it deletes them, occasionally it creates them, and eventually, when it goes out of scope, it also deletes them. When we have a box like this, stack concept that we're using today, we say that this is actually a resource manager, because majority of its work is actually to make sure that this dynamically allocated block of integers is managed properly, right? So, and we were able to do this with the two functions. Allocate memory simply says, okay, we want to have a new block of memory, and this is the size. Whatever we decided to have the size, it will be accomplished by this function called allocate memory. When we say reallocate memory, in this instance, we create new block, have a temporary pointer that holds the address of that new block. Then we created a loop where we copy elements from one dynamic array to the newly allocated one, right? And then we delete the old memory block, and we simply say that the memory block is now should be pointing to the location of the new memory block. In this way, we can reallocate the memory. And we can see that if we push, let's push like 4 elements on the stack, 11, 22, 33, and 44, right? And if we keep doing this, and we can do pop later on, I don't know, or like somewhere here. If we keep doing it, right, so if I build this again, and if I run it, you can see that the memory got allocated initially, and the initial capacity was 1, which was capable of accepting element 11, integer 11. But as soon as we went to push 22, push detected that the capacity was already reached by the current size of the stack, and so it decided to double the capacity. So we went from 1 to the capacity of stack 2, right? Then as we pushed 22, again, very soon, the capacity was reached, and then we doubled the capacity and made it 4, and we're still able to accommodate 44, and it was at the top of the stack, and the size of the stack was 4 elements as well. So we went through this type of tracing messages, and I showed you how you can have this function symbol to visualize the name of your function from inside your code, right? So this essentially makes it look like this, in stack allocate memory. So allocate memory, just like the reallocate memory, are functions that belong to the scope of this in stack class. And the full name of the function is in stack : allocate memory and others, which basically this : is called a scope resolution operator. So it simply just says that allocate memory thing should be found as a member of in stack. What's in stack? compiler will know that this is actually a class name in stack, which has many things in it. All right. So, okay, new thing. So we've done this thorough overview of what we already have. The concept is such that it works, it allocates memory, and this first or second version of this program, it seems to be okay. Now, I'd like to preserve this version, and I'm just going to say window, close all of this. Then I will say build, clean the solution, say file, close the solution. Then I'll jump to the, I think I'm still running it, so I need to dismiss that as well, right? I don't need that, right? So this is the project directory. I will delete the debug, just hit delete key and say delete yes, and then delete the SDF file because it's big, 7 megabytes. I don't need that. I will just delete that. Everything else you need in this project. So then I go back to the upper level, and I will simply make a copy of it. I will just say copy and paste in the same location, and I will rename this to be rename. This is officially, this will be version 3 of the stack, version 3, and this is week 10, so we're consistent in naming things. So I'll just simply rename this, right, and just make it like that. So I just cloned the version 2 to be version 3, and now I will just go File, Open, and open version 3, which is copy of version 2, right? So this is version 3. I still opening version 2 inside the solution, and open this file. Go View, Solution Explorer, and here I can try renaming things, right? So I should be renaming my solution now to be just version 3, and this is week 10, right? Just do that. Inside this Visual Studio thing, right? So if I right click again, I can say rename again, and again say week 10 version 3, and the rest of the files will be fine. So at least I got some meaningful naming preserved so that I'm not lost in the way I'm naming those things. But I decided to preserve the prior version and go with this new copy of what we had. All right, so just going to say File, Save All, right, and then we're just going to say project, build this project, right? Build this project. It builds fine. I can run it. It runs the same way. So I'll just change the properties again very quickly so that it's easier for us to navigate through everything here. Right. So the colors. Update the colors. Very well. Okay. So this is the same thing, but we have preserved the older version. Now, it's interesting that when I say push 11, 22, and 44 on the stack, those integers are dynamically populated inside that dynamic memory array that I allocate, right? So right here, we can say that basically what I get is like 11, 22, 33, 44. All of these values are dynamically stored, and once in a while we actually reallocate the memory to accommodate more integers in computer memory, which we allocate dynamically by new, and so forth, right? But we already know that since the day we started to use structures, which were essentially a facility that came with C programming language, we can say in stack, and we can say in stack, stack2 equals stack. Okay. So this is called a copy. When something like this happens, the compiler generates the code like this, right? So we have this stack that we named ST, our first stack, right here, stack ST. Then we create another stack named ST2, right? So we would like to create another stack ST2, so I will draw the box somewhere here just to make sure that we're looking at another instance of the stack. But once again, it's going to occupy the same memory with zeros and ones somewhere in memory, right? So it's going to be given a place in memory to exist. And the default version of this copying since the day of C programming language, right? What happens is that the original zeros and ones are essentially, each bit is copied over to essentially make an exact binary copy of the original object. So this becomes 0, 0, 1, 1, and 1, right? So they become identical, right? So physically, they become identical, and that's the result of me actually creating a second stack in my function here. So this is quite similar to, remember how we could say integer x equals 11, and then we can say integer y equals x, right? So similar stuff. If we could make a copy, initialize and create variable y, we could just basically provide the value of another variable to it. Similarly, we create a second stack and populate it with whatever bits the original version had, right? So that's quite similar. Okay, so but what happens in logical view is that because this because the memory block variable somewhere here inside the copy, so we made a copy of this, right? So we manufactured the copy of zeros and, using zeros and ones. That's the default behavior. So interestingly, this memory block of ST2, this is ST2 box, is going to be pointing to the same memory because it's just going to get, if this was an address of the memory block, it's exactly the same. So logically, it's pointing to the same memory block. And this is what we call a shallow copy, which is generally speaking in many cases, especially in the current case, is a bad thing. Because let me demonstrate this, right? What I could do is that I could do this copy somewhere like this. I could say void use stack, okay, and pass int stack by reference, right? So the original stack is passed to a function by reference, just like this. And all of a sudden, inside this use stack, what I do, I make a copy of it, right? And I do something with the copy or whatever. So let's consider this. So if I wanted to call function in use stack, stack, and pass my stack by reference, the stack that I already have, right? So I already have an object named stack. I call use stack. I pass st. Look what I did just to demonstrate the capability. I can pass the stack by reference. So of course I'm not making a copy of it. I'm passing just symbolic name of the stack internally. Of course, it's using the address of the original stack. But look what I do here. I create stack 2, and I say, let's have it as a copy of stack 1. So this happens now, but look what just happened, that stack 2, right? Let me just switch over to maybe a different color, right? Stack 2 and stack 1 are now in different scopes, right? Because this was the scope of main right here, and this is now the scope of use stack, right? And I found a way to make a copy, ST2, of the original stack, but in a different scope, because indirection, such as references, allows me to do these types of tricks. What happens now is that by the time I reach this closing brace of use stack, this stack 2 is going to be destroyed, okay? So stack 2 is going to be destroyed, which is pretty much like this, right? So it's just going to go, and basically all of this is going to be wiped off. It's going to go away, right? Okay, looks innocent enough, but before any of the object of type in stack goes away, its destructor is invoked. Let's take a closer look at our implementation of our destructor, which is inside this in stack, right? So let's resize this and show it side by side, right? So if you look at this, you realize that the destructor of in stack tells memory manager, free this memory block, right? So before this, before the second copy, right? Before the second copy of this in-stack ST2 got destroyed, it actually told memory manager to free this memory, right? To free up this memory. So this memory is now gone. And you will see now the problem that now we're returning back to the main function, and we're trying to still use it, like access the top element, look at its size, and perhaps I could do something else here. I could attempt to push yet another element on the stack, and guess what? This program may crash or may not crash, but because our concept of the stack is still not fully developed. It has this big problem in its implementation, that copying of it is completely unsafe. So let me say, let's test this and see how it actually behaves.